Welcome, honors chemistry students, to tonight's acid-base review session. Waiting for our first question to pop up. I haven't gotten really anything via email today. I hope that the review sheets and everything were helpful in class. Sorry I couldn't be there, but I had a sick kiddo at home today. While we wait for the first question to come, a couple of things to keep in mind about the test tomorrow. Remember, it will be multiple choice and short answer as always. So you will have part multiple choice, part short answer. You do get the square of awesomeness on the test tomorrow, so you just have to know how to use that square. So just make sure you're following the correct arrow when you're going between the different concentrations of either H plus or OH minus, or if you're going from pH to POH. So the square of awesomeness will be copied right on your Scantron for you. You do not get the Mavaba equation, so you will need to memorize that. Just make sure that when you are doing Mavaba, that you keep the molarity of the acid and the volume of the acid on the side with the mole ratio, and you have the molarity of the base and the volume of base on the opposite side. So just a couple of reminders about that. And the review is posted online with answers if you have questions about that, and I will broadcast here tonight for about the next 45 minutes. Unless no one shows up, then I will stop broadcasting at that point in time. But remember to ask a question tonight for the review. Please make sure that you type it in the comments box, and if you are not logged in with the comments options, you can shoot me an email, shannon.etnier@d128.org, and your question will come on up through the email as well. So those are the different ways that you can go ahead and submit questions for this evening. And if you have a question that pops up and the review ends, remember you can always swing by tomorrow morning. I will be in my room. But it looks like we have our first questions. Let's go ahead and see what we got. Welcome to the review, guys. All right, first question. How to recognize whether or not something is a buffer from two given substances. Awesome. So let's go ahead and let's start there. I'm going to start by sharing a Word document with you guys. If at any point during this review my face pops up and the Word document goes away, someone please comment and let me know. That happened in my first review where I thought everyone could see what I was writing and no one could. So just let me know if that happens. So the first question I got was example of how to tell whether or not something is a buffer. All right, so that's a great question. So I'm going to go ahead and give myself some space here so I can type in the next question after that. So how to tell something is something or not is a buffer. Well, a couple of things you want to keep in mind when you're trying to determine if something is a buffer or not is first you want to ask yourself what types of acids are present. Because remember, a buffer can only be made of weak acids or weak bases. So if you were given a list and in that base you saw any of those strong acids that you had to memorize, so HCl, H2SO4, HNO3, H3PO4, HF, HBr, HClO4, just to name an example, if you see any of those ever asked as, is this a buffer system? It cannot be anything with that strong acid, or conversely, it could be nothing with a strong base. So anything that is an OH ion stuck to any metal from column 1 or column 2 except beryllium. Now, the other way that you would have to identify if something could be a buffer or not is looking for the conjugate acid base pair. And this seems to be one of the biggest sticking points on this test. So it must be a conjugate acid base pair. So I'm going to give you an example of one that would be and one that wouldn't be. And we're going to deal with the phosphate ion. So if you were given the potential buffer system that was NaH2PO4 with Na3PO4 versus NaH2PO4 with an Na2HPO4. If these were the different options you were given on the test tomorrow, one is a buffer and one is not. The one that is a buffer, the one that would act as a buffer system is this guy here. The guy that would not act as a buffer system is this guy. And here's the reasons why. When you have something that is a buffer system, it has to be that weak acid or base that is a conjugate acid base pair. So when you're given these things, if you ever see an ionic compound in front of it, just go ahead and cross out the metal ion. The only reason those guys are there are because we can't buy these negative pieces from the store, so we can only buy them in the form of a salt. So this guy would be an H2PO4 minus ion. If I take away these 3 NAs over here, this would be a 3 minus ion. And if I take away these 2, this would be a 2 minus ion. So the reason this top one would not be a buffer system is because there's too many H's that are removed. When you're looking at a conjugate acid-base pair, it's the loss or gain of 1 H. So if we look at this top example, for me to go from H2PO4 to PO4 3-, I have to lose 2 H's, which is too many. That's too many for a conjugate acid-base pair. This would be our buffer system because it has 2 H's on the acid side and only 1 H on the base side. So this would lose an H to turn into an HPO4 with a 2- charge. So this has only lost 1 H, so it would in fact be a buffer. So I hope that helps. If you're looking for something is a buffer or not, first determine do you actually have a weak acid or base present. And then if you do, make sure it's a conjugate acid-base pair. All right, our next question that we have on the review tonight is, how is the number for 17D? A few classmates and I got the answer C. So number 17 on the review sheet. All right, let me go ahead and pull that up. I actually don't have it at home with me right now because I was homesick today with the baby. Sorry about that, guys. So I'm going to pull that review sheet up. As I said in my sub notes, I don't know if those actually got to you. I was not 100% certain that it was actually the right answer. So let's go ahead and check and make sure I didn't screw something up, which is totally possible. So if we look at that review sheet here, all right, number 17. Number 17 says, based on the graph, which of the following is true? At the equivalence point, the H plus is greater than the OH minus. The titration curve indicates the unknown liquid is a weak base, and C says the titration curve indicates that the unknown liquid is an acid. And D is the equivalence point is log base 5. So I'm just going to go ahead. I'm going to copy this picture in there. Actually, I'm going to do this real quick. Let's just put that question right in there. Sorry, this is kind of being a pain in the butt right now. Let's try this again. I apologize for the delay. No, wrong one. Save, desktop. You guys are listening to me talk through all this. How exciting is this for you? You can totally make fun of me right now. Sure, let's save it right there. There, you must include a, okay, well, let's do this then. My computer's yelling at me right now. Okay, there we go. All right, and Adam, sorry for the delay. I should have had this up beforehand because, you know, that would be the smart thing to do. So here we go. Number 17 on the review sheet is coming at ya. Let's go ahead and just copy and paste this guy in there. Okay. Copy and paste. All right, so number 17, the correct answer is not going to pop up. Do you want to paste? Is on the next screen? Oh, it is down there. Look at this. Found it. Okay, so let's delete this guy here. So number 17 is asking about how you know that the unknown solution is an acid. So if we look at this titration curve right here, you can tell that the solution that's being used was an acid because the pH starts low down here. So this starting point, this starting pH is going to tell you, let's go ahead and cancel that. The starting point is going to tell you whether your unknown is acidic or basic. Because my pH is starting so low, that means that I must be titrating an acid. The other hint here is because on the x-axis, it tells me that I'm adding NaOH to an unknown acid. I must know that that unknown is acidic in nature. If we were titrating a base, our pH would start high and then end low. So that's how you know on number 17 that the unknown is acidic in nature, because that pH is low and it also tells us on the y-axis. So I hope that you found that question helpful. And those are the only 2 questions I have right now. So if you are someone who is currently watching the video that does have a question, feel free to either type it in the comments box below or to or to go ahead and email me the question. I guess I can type my email on the screen for those of you that may not have me as a teacher. I know some of Mrs. Staub's students are watching today. So if you do have me, Mrs. Staub as your teacher, you can still shoot me an email. My email address is, I should probably just write it on the screen. Email Shannon.Etmeyer@d120.org. All right. Let's go ahead and backspace. All right, let's go ahead and enter down. And let's take our next questions. We've got a couple more questions that are popping up. Lovely, lovely. All right, our next question is, could you explain how to prove through salt hydrolysis if it's acidic, basic, or neutral? All right, so how to determine if a salt will be acidic, basic, or neutral. Okay, so when you're doing salt hydrolysis stuff and you're trying to figure out if it's acidic, basic, or neutral, what you want to do is you want to look at what the salt is made from. So for example, if we have, we can talk about the guy we were just talking about up there. So if we had Na2HPO4. So when we look at what this salt is made from, this salt comes from, Na is the conjugate acid, so that means the base had to be NaOH. This HPO4 is going to be our conjugate base, which means it came from the acid. In this case, our acid is going to be H2PO4. So if we look at this, this is a strong base, and this is a weak acid. So that means that this is going to be basic in nature, and the reason being is why. When we have a weak acid, that means this HPO4 part is going to be a strong conjugate base. So if we were to go ahead and we were to try and actually write what happens when this dissolves in water, because this HPO4 is a strong conjugate base, when it's put in a solution with water, it wants to go ahead and it wants to take that H back. So this HPO4 is going to snag one of these H's from water, and that's going to leave OH minus ions floating around, along with H2PO4 weak acid particles. So this is why the solution becomes basic. If we were to do a different example, if we were to do one that was going to be a strong acid and a weak base, that would be like ammonium chloride. So if we had ammonium chloride, for example, when we look at what this does in water, this comes from NH4OH, which we know is a weak base. And the Cl comes from HCl, which is a strong acid. So because NH4 is a weak base, that means, because this NH4 is a weak base, that means this must be a strong conjugate acid. So we're going to go ahead and we're going to be able to show how this dissolves in water. So if we put that NH4 plus, because it's going to be a strong conjugate acid, when it's put in water, it's going to give up an H plus, turning into an ammonia particle and a hydronium ion. And because we have that hydronium ion present, that's how we end up with an acidic solution. So tomorrow on the test, if you're asked for proof, basically the first thing you want to do is you want to figure out what's stronger. Is the base stronger or is the acid stronger? Because that's going to be what your solution is going to be. So if I'm a strong base, that means it's going to be basic overall. If I'm a strong acid, that means I'm going to be acid overall. Then the part that's weak is going to be the one that interacts with the water. So because I was made from a strong base, this back part is going to be the one that picks apart the water molecule, leaving the ion you need behind. So if you have a strong base, your solution has to end up with OH minus ions. And if you have a strong acid, your solution has to end up with H3O plus ions. I hope you found that helpful. I hope that answered the question that we had. So if it didn't, please resubmit your question and let me know, hey, Atnar, that did not answer my question. But my email is blowing up right now. So let's go ahead and pull our next question. Oh, geez, sorry. Okay, got that one. Sorry, I opened too many at a time. So now I'm going backwards, making sure. What is the difference between an acid-base theory? All right, great question. So what are the differences between acid-base theories? So if we are going to go ahead and take a gander at acid-base theories, let's go ahead and use blue. So there's basically two acid-base theories. We've got Arrhenius, I'm just going to abbreviate AAH. We've got Bronsted-Lowry, who I'm going to abbreviate BL. And so if we think about that, you've got your acid theory and you've got your base theory. So if we were to make a little table here, similar to what we did in notes that day, I did not use a ruler, don't make fun of me. So if I'm in Arrhenius acid, he says that you must produce H+ when dissolved in water. Where Bronsted-Lowry said you must be an H+ donor when put in water. So really, these two things are not saying anything that's too terribly different. All they're saying is you have to be able to make an H+. So that's how we know acids are going to be compounds that have H's in the front. Where they differ is in their base theory. Arrhenius said you have to produce an OH- when you dissolve in water. Where Bronsted-Lowry just said you have to be able to accept an H+. So this is where the difference comes in. If we think about an Arrhenius definition, Arrhenius said your compound has to have OH- in there. So NaOH, BaOH2, MgOH2, those would all be examples of things that are Arrhenius bases. Where Bronsted-Lowry broadens that definition. You don't have to have an OH, you just have to be able to accept an H+. So if we think about ammonia, when it's put into water, because it's a base, it can accept an H from water, and that makes OH- ions when it dissolves, which is why the solution ends up being basic. So this is the big difference between the theories here, is Bronsted-Lowry says you have to be able to accept H+, where Arrhenius said you have to be able to make OH-. I hope that helped. On to the next question. I just want to say right now, you guys are blowing up my email. And that's absolutely cracking me up, and I love every single minute of it. Okay, so I had a question based off the question that I answered earlier about the titration curve. It says, would a titration graph on an increase always be representing an acid? And I believe, Shashank, I hope I said that correctly. You are 100% correct. If we go back to that titration curve, anytime you see a titration curve that has a graph with an increasing line, that would indicate that it's going to be an acidic solution, because your pH is starting low and ending basic, meaning you're adding your base from your burette into your acid that would be in your flask. So an acid would always be titrated with a positive titration curve. A base would always be titrated with a negative titration curve. So great extension to that last question. Oop. All right, I've got another question about the review sheet. Someone asked, how do we solve number 29 on the review sheet? So let's go ahead and take a quick look at what number 29 is. All right, 29 says calculate the pH of a 0.35 molar hydrochloric acid solution. So let's go ahead and solve that problem. Oh, sorry. So pH of a 0.53 molar HCl solution. Okay, so this one's going to be using your square of awesomeness, which remember you do get on the test tomorrow, so you just have to be able to use the equations appropriately. So because it tells me I'm 0.53 molar of an HCl solution, and we know that HCl is a strong acid, basically what we can read this question to say is I've got 0.53 molar of my H+, because this is going to fully dissociate when put into water. So I'm pretty much starting with 0.53 molar H+, so I just have to solve for pH using my square of awesomeness. So when I'm going from my H+ to my pH, I'm doing the opposite log function. So in my calculator, I would put opposite log of 0.53. And when I do that on my calculator, whoop, it tells me that my pH is 0.27. Let's see, I've got 2 sig figs, so 2 decimal places, so 0.28. I think I might have actually chose the wrong answer on this because I did it super fast. So it's 0.28 would be your pH for that. So Scott Blake, I hope this helps you. And if this is not the answer I have in my answer key, I apologize because I probably just put the wrong answer in because I did it in like 5 minutes because baby was sick. All right. Let's go ahead and get ourselves a new page break here. I'm going to erase some of the stuff on this slide. Yeah, while I get the next question up at the same time. No, maybe not. I hope you guys are laughing at me at home right now. At some point here in the near future, I might have to take a quick walk away from this. My husband was coaching track tonight, and he is not yet home. So when he does get home, I have to let the dogs out. Otherwise, they'll wake the sleeping baby. So I will give you a heads up when that is coming. But let's go ahead and take the next question. All right, next question on the video is the rule that you can only remove one H plus ion at a time only for acids or for bases also? And this is coming from Jessica. Jessica, that is a fabulous question. The rule is for acids, you can only remove one H plus at a time. So rule for removing H plus and OH minus. All right, so the rule is with acids, you can only lose one H plus at a time. This is why we write those. Equations. So like if I had H2SO4, we show the ionization happening in steps. So the first step, H2SO4 is going to act as a strong acid. It's going to break apart into HSO4 minus and H plus. Oh, that's a plus sign, not a minus sign. All right. And then the second ionization is going to be where we have the reversible situation happening because this HSO4 is actually a weak acid. So this would be the ionization of H2SO4. It does ionize in steps. Your bases, however, we're just going to lose them all at once. So lose all that's not an H. Lose all OH minuses in one step. Because these guys are ionic compounds that are solids in nature, so they're going to ionize like a regular ionic solid does, just like NaCl. So if I had MgOH2 that I was dissolving into water, it is going to ionize into Mg2 plus ions and two OH minus ions. So it's just going to do it all at once. So acids will only lose one H at a time, where bases are going to lose all their H's at once. All right, on to the next question. All right, so I've got a question about a buffer. So talking about how it will absorb acid or bases when it's added. So the example buffer that was asked was about NaF and hydrogen fluoride. So NaF and HF. So how does buffer work? How does NaF HF buffer absorb H plus and OH minus? All right, so I'm going to draw a picture first. I'm going to write some equations. So in our buffer bucket, so if we were to go ahead and draw a buffer bucket, we would have two pieces to that buffer. We would have some Na ions and some F ions, and we would have some HF pieces. We're going to go ahead and switch our colors up. Let's go purple. All right, so that would be what we would have in our buffer. And so we have each of these pieces in our buffer because they can react with the acid or the base. So since the HF is going to be the acid part in our buffer, it will react with any base that's added. And because the F minus part is going to be the base part of our buffer, it's going to react with any acid that's added. So let's go ahead and let's look at that F minus first because I'm in green. So if I add HCl, the important part of the piece that I'm adding is an H plus because HCl is a strong acid. So when I add an acid to a buffer, it's going to react with whatever your conjugate base is, and that's going to form, in this case, an HF particle. And so the reason that your pH is not going to change for your buffer is because we do not allow the accumulation of those H+ pieces in the buffer system. So they're going to be grabbed up by the base that's in your buffer, making these weak acid particles that are going to mostly remain together. So we know that weak acids do sometimes slightly ionize, but not a significant amount. So we might see the pH of this drop just a smidge, but it's not going to drop like when we add H+ to just regular old water, because these base particles that are in that buffer system can go ahead and absorb all the I guess up to the buffering capacity. They can absorb all those H+ that are added. So if we add an acid, this is what the reaction would look like. Whoop, that's how you spell acid. Yikes. All right, if we were to add a base, so if we were to add OH- to the buffer system, this is why we have that acid particle in there. Oh, that's not an H. Oh, yeah, I'm sorry, kids. I'm struggling right now. Ooh. So when you have a base in a buffer, that's going to react with the acid part that you have, because we know bases like to grab H+. So that's going to go ahead and that's going to grab that H+ to make HOH, which we know has a neutral pH, so it's not going to change the pH of the water that much. And that's going to leave behind your F- piece, which we know is the other portion of our buffer. So when you're doing a buffer, you have an acid and a base part so that you can react with any acid or base that's added. Any added acid will react with the base in your buffer, and any base that's added will react with the acid in your buffer. And because these are able to absorb those particles, you don't see a significant change in the pH. Now remember, all buffers do have a limit. They do have a maximum capacity they can hold, just like a sponge has a maximum amount of water it can hold. These aren't going to be able to absorb acid and base forever. Once they reach their maximum, we will see the pH change. So I hope that helped with the buffer question. And if not, go ahead and resubmit a follow-up question, but I hope that you found that helpful. On to the next. All right, someone asked, can I have an example of an Ka-Kb problem and walk through it? Absolutely. Let's talk Ka-Kb. I know there's one on your review sheet. Let's go ahead and do a page break here. Give ourselves some room for some Ka-Kb fun. So on your review sheet, I believe a Ka-Kb problem is like number 34 on your review sheet has a Ka-Kb problem. So number 34 says, so this is number 34. So this is Ka-Kb ice table. This is number 34 on the review. All right. So the number 34 says the Ka of benzoic acid is 6.3 times 10 to the negative fifth. So we've got, no geez. You got 6.3 times 10 to the negative fifth. Come on, equals Ka. And it says, what is the equilibrium of H+ in a 0.2 molar solution? So our benzoic acid is C6H5COOH. So C6H5COOH. So when that ionizes, when that reacts with water, remember we don't care about the water piece. It's going to turn into H3O+, which we know is basically just the H+. And it's going to turn into C6H5. Oh, that's not an H. Sorry, you can totally laugh at me right now. C6H5COO-. So this is the ionization of that. So we can write our ice table, ICE. We scribble out the water because the water does not impact our Ka. And if we go back and we pick out the pieces that we need, we want to know what the H+ concentration is in a 0.2 molar solution. So what we know from the problem is we know that we're starting with a 0.2 molar solution of this. And initially, when I'm first making my solution, my ion concentrations before I even start are 0 and 0 because I'm all reactant and no product. So when I am establishing equilibrium, if I don't know what these variables are, I can go ahead and I can put X in for them because the ion ratios are all 1:1. If I make my H3OX, that means my C6H5COO is also going to be X, and then my change in my acid is also going to be X as well, because these are all 1:1 ratios. If these were not 1:1 ratios, we'd have to have some variables like 2 or 3 in front of here, but we save those for the AP kids. So now we have to decide what's happening to our X variable. Because we're starting with all reactant and no product, as the reaction goes, my product ions are going to increase and my reactant ion is going to decrease. So I can go ahead now and I can figure out what's going to be happening at equilibrium. So at equilibrium, I'm going to have a concentration that's going to be 0.20 minus X for my acid, and I'm going to have the concentration of X for each of my hydronium ion and my conjugate base over here. So if we were to go ahead and put this up into Ka, we can write our expression. Ka is going to be equal to the concentration of H plus times the concentration of C6H5 COO minus all over C6H5 COOH. Now, because this X variable is not going to change this numeric value based on sig figs more than 5%, we can go ahead and we can get rid of this variable here. And so now we can plug in what we know. We know our Ka is 6.3 times 10 to the negative fifth. That should be a negative sign there, just didn't transfer over. So 6.3, come on, times 10 to the negative fifth. We can set that equal to, since each of these variables are going to be X, I'm just going to call it X squared. And on the bottom is going to be my 0.2 molar. So then to solve for X, what I'm going to do is I'm going to cross multiply my 6.3 times 10 to the negative fifth times 0.2. And then because I'm X squared, I'm just going to simply take the square root of that answer. That's going to get me to an X concentration of 0.003, let's take 2 sig figs, so 0.0035 molar for my H plus. So that would be the answer to this problem. Now tomorrow, if we asked you for the pH, let's say, what would the pH resulting situation be if we wanted to take this one step further? What we could do to go from just my H plus to my pH then is use our square of awesomeness. So we would simply just take the opposite log of 0.0035, and in this case, negative seconds, that would give me a pH of 2.45. Now remember, just a quick refresher of sig fig rules for pH. However many decimal places you have in your concentration, or sorry, however many sig figs you have in your concentration, that's going to equal the number of decimal places you have in your pH. So if you have 2 decimal places in your pH, that means you had 2 sig figs in your concentration. So that's just a quick reminder for sig fig rules tomorrow for your test. So I hope that this helped you with a Ka-Kb problem. All right, I can have a general question. How do you know if the reaction is reversible or not? How do you know if the reaction is reversible? Reaction is reverse. Sorry for my terrible handwriting, by the way. So how you know if the reaction is reversible is all about the strength of the acid. So if you have a strong acid or base, that means that you're going to have a non-reversible reaction. So I mean, it might go backwards just a little bit, but it is mainly going forwards. So this would be forward. If you have a weak acid or base, then you have a reversible reaction. So reversible reactions are only going to be for weak things. Strong things will only go forward. And I hope that answers our question about reversible reactions. Let's go ahead and get ourselves a new page here and on to the next question. Can you explain when acids do not have an H plus at the beginning of the formula? You will see some acids, like the example that I just did, that benzoic acid. So when acids do not have H in front. So just like that example I just had, that was C6H, but it's not an H, it's a 5. C6H5COOH. This guy back here is called a carboxylic acid. And it's going to be this H back here that is the acidic acid. I should say the acidic H. So that's going to be the H that's lost. So this is a car. Sorry, my pen is like having half the words go away. So that's going to be a carboxylic acid. So that means your H is actually going to be in the back, or if we think of something like HCl or H2SO4 or HNO3, all of those things have H's that are in the front. So if you see the COOH on the back, that does mean that you have an acid. It's not a base. So normally you'll have H's in front, but this guy COOH, do pay attention for him tomorrow on the test because that does mean acid. And Jacob, I hope that helps you out. All right, the next question we have is, how can you tell the difference if an acid or base is accepting or giving an H or OH, and how to tell if it's an Arrhenius acid base or a Bronsted-Lowry acid base? So we talked about acid-base definitions in the beginning, and how you would know if it's giving or receiving an H is you have to read the context clues in the question. It's really going to be the most important part in terms of you being able to identify what it's doing. So oftentimes in the question, it will ask something like, in a situation where this is, acting as an acid, or what is the conjugate base for this acid? So for that part, it's really about reading the question carefully. But the other way you can figure out if it's giving in or taking an H is by looking at the chemical reaction. So how do I know if it's giving or taking and H? Okay, so what you really want to do is you want to look at the chemical reaction itself. So if I have HSO4 minus in water, on the test tomorrow, we would not ask you something like, is the HSO4 going to be an acid or a base? Because there's no way you can tell. Because it has an H in front, this would be an impossible question for you to answer. The only time we would ask you a question like that is if you had an uncharged particle. So if you had like H2SO4 or H3PO4 or HClO4. These are the only times you can know something is for sure going to be an acid, because the acidic H is in front. It's going to have an acid name like we learned from our naming rules. So these things are going to lose H's. But when you get into some of these situations where you have polyatomic ions with H's in front, it's really hard to know, is it acting as an acid or a base? So you have to use the context clues of the chemical reaction that's provided. So in this case, if I wanted this to act as an acid, this would give my H to my water. So my resulting reaction would be SO4 minus and H3O plus. Your context clues for knowing that this is acting as an acid is because it's losing an H as it goes to the product side. So it's got to donate it somewhere. And because our water went to H3O plus, that must be where it went. So this is how you would know if that HSO4 was going to be an acid. Now I'm going to take a quick 2-second break and finish answering your question, Lexi. I have to go let my husband in the house so the dogs don't bark at him. All right, boys, come here. No, no, no. All right, and I'm back. I apologize if you heard a baby crying in the background because the dogs barked, or if you hear dogs barking when my husband comes in because they're nuts. Okay, so how will we know this HSO4 is acting as a base? If I have that same HSO4 and I have it reacting with that same water, it would act as a base if its H plus goes up. So if it turns into H2SO4 and then an OH minus. So you would know that's acting as a base in this case because its H plus number is going up. And if you notice on the product side, if something's acting as an acid, you're going to see an H3O plus. If something's acting as a base, you're going to see an OH minus. So those are just a couple of hints to help you guys out tomorrow to determine if something is acting as an acid or a base. Do you want to come say hi to the kids?
Oh.
All right. My husband's going to come around and say hi to everybody. He is very, very tired. He just got done coaching.
My message to the children of the world today is don't get stuck at a track meet with the slowest starter on the planet.
He's a very happy camper. I hope you like that 2-second memory. He's very tired and cold. Okay, back to chemistry. Uh-oh, this is what I want. Okay, this is the right screen. And we're back to the questions. Okay. Oh, geez. What did I do? I screwed up the chili. I did. Did it go away? I burnt the chili. Kids, I burnt the chili. You burnt the chili. Oh God. Bill, can you please come show it to the kids? Because they're gonna be like, what is going on? While I was running this review, I forgot that I left the chili on the stove.
So, my new message to the children of the world.
You have to show them.
You can't eat this. This is burnt. This is like, this pan is dead.
I can teach, I can't cook. What can I say?
It's like,
I'm sorry. I thought I had it on low. Oh. Okay, back to chemistry. Yeah, I hope you guys are all laughing at home right now. Ay, ay, ay. Happy Monday for my husband. He has no food to eat. All right, how do you do number 20 on the review sheet? So let's pull up number 20. All right, number 20 says, which of the following acids could be the unknown solution, given that the unknown solution had a volume of 50 mils and a concentration of 1.25 molar? So this is going back to our titration curve problem. So a couple of things we need to know. So if we go back to this guy here, I don't know where I put it anymore. I'm like 16 pages in. Okay, so a couple of things that we need to keep for this problem here is, we know that this Sturdy Epi Downy is our equivalence point. So if we follow this down here, we're in between 10 and 15. So this is going to be 13 milliliters. And then I know that it's 0.1 molar. So for my base information, what page am I on right now? I'm on this guy here. So for my base information, number 20, oh, that's not how you spell on. I know that my base is 0.100 molar, and I know that it took 13 milliliters to get to the equivalence point. So I knew that information going in. So the rest of the problem tells me that the volume of my acid had 50 milliliters and a concentration of 0.0125 molar. So I know that my acid information is it was 50 mils and it was 0.0125 molar. So we think about ma ba ba or from Stubbs class, ma ba da ba da ba da ba da. I know that the molarity of my acid is 0.0125. I know the volume of my acid is 50 milliliters, and I don't know my mole ratio. I know that the volume of my base is 13 mils, and I know that my molarity is 0.011 molar. So if I solve for X, I'm going to do 13 times 0.1 to get 1.3. I'm going to divide it by 50 times 0.0125. And that gets me an answer that is roughly 2. So when I think about this, I know it's the base over my acid is my mole ratio. So it tells me that my base coefficient has to be a 2 and my acid coefficient has to be a 1. So when I look back at the list, I'm looking for a diprotic acid. And so the only one that's a diprotic acid for number 20 is choice D, carbonic acid, H2CO3. So that is how you solve number 20 on the review sheet. And a couple of people had questions on number 20 on the review sheet, so it seems like that got that problem knocked out of the way. All right, our next question is about drawing the titration. So it says, can you please explain how drawing the process of titration changes as the titration progresses? For example, before the titrate is added, 1/3 of the way, 2/3 of the way, and the max amount added. Absolutely. So let's go ahead and let's draw some titrations. Fabulous question. Let's get ourselves a new page here. All right, so I'm going to draw myself 4 beakers. Honey, I'm sorry I ruined dinner. The kids are probably going to make fun of me tomorrow, just so you know. So this will be start, 1/3, 2/3, end. So if we are titrating an acid to start, what that means is we have all acid particles present. So since we're doing thirds, I'm going to draw 3 acid particles. And I'm going to draw 3, it's going to be HCl we're titrating. It could be, oh, you know what, we're going to do it less specific. We're going to do any generic acid. So we're just going to make it HA. A just means that, hey, I am a generic acid and I am putting it in there. So if I'm 1/3 of the way, if the base that I'm adding is NaOH, so I'm going to add NaOH to all these guys here. That means it's the OH minus ion that's what's really happening. So if I had 3 H pieces to start, 1, 2, 3. So if I am 1/3 of the way, that means one of my H particles has reacted. So I'm going to add an OH to it. And when those things react, we know they make water. So 1/3 of the way means I would have 1 H reacted to make water, and I have 2 H pluses left. I would still have 3 A minus guys in solution. And I would have now 1 Na ion in solution because I've only added 1 OH to react. So if I'm thinking of 2/3 of the way, I have 2 H particles left in there. Whoop, whoop, whoop. I have the Na guy that I added before. So if I add another OH, we're going to make another particle of water. And I'm going to bring another Na into the mix because I had to add another NaOH to go ahead and make my water. And then at the end, what that means is all my acid would have reacted. So I will have 3 water molecules. I would have 3 Cl minus ions. And I would have 3 Na ions, because all of my Na and all of my OH would have reacted. Now, if we talk about what's happening as pH changes here, because I'm all acid here and that's it, and it's just acid and water, my pH might be really, really low. So we might call it like pH of 2 or 1 to start, depending on how concentrated we are. As my H reacts, my pH is going to get a little bit closer to neutral. So my pH here might maybe be like a 4 or 5. And then as I get even closer to neutral, when I only have 1 H left, my pH here might be a 6. And then when I hit my endpoint, as long as it's a strong acid, strong base titration, my pH would go ahead and end at a pH 7. So as we add in a particle, we're going to have 1 more H reacting in each picture until we have all water and no H's. And at this point, if we were to go past the endpoint, because there's no H pluses present, the more base we would add would continue our pH to increase and increase, which is why we see that upper end of the titration curve becoming more basic. So I hope that answered your question. All right, we've got just a couple more questions here. I know I've gone a little bit past the time, so if you're still with me, thanks for staying. I got 3 more questions, it looks like, in my email. So if you have that last minute question, maybe get it in before I answer these last 3, because if I don't get any more, we'll be ending after these next 3 questions. So someone just asked, hi, Mrs. Etnayer, can you please explain the difference between neutralization, equivalence point, and titration? Well, there's really no difference between those 3 things. It's kind of about what's happening. So the process of this is what we call titration. So by adding our base to our acid, you are doing the titration process. Your titrant would be the base because it's in the burette, and you're using it to analyze a solution to figure out its concentration, which would be our acid in this case. So this would be the process of titration. Our goal in a titration is to end up, as long as it's strong acid, strong base, is to end up with a neutral solution. So we sometimes call titration neutralization reactions because our point is to get with a pH of 7. And the end point is going to be when your moles of H plus and moles of OH minus are equal. So I've added equal amounts of H plus and OH minus. That's how you know your end point. So titration, the process that we're doing, neutralization, when we end up with that neutral solution with a strong acid, strong base titration, and our endpoint is when our moles of H plus and moles of OH minus are equal, which is what we see at our pH of 7. So I hope that helped you. All right, someone asked, how do you know if an acid or base is going to gain an H or lose one? So if we go back to this guy here, like I said earlier, it's going to be about the context clues in the question. So it will ask you things about how this acid will react in water, what will it look like if it's losing an H plus. So you have to really read the context clues. It's really hard for me to say if it's going to lose an H or gain an H because each question is going to vary. But the only really tricky ones are these guys here. And like I said, we would give you some sort of reference to help you know. So we would ask you maybe for the conjugate base, which would mean this would have to be an acid. Or we would ask you for the conjugate acid, which would mean this is going to have to be a base. Or we would flat out give you this reaction in water. So I'm sorry I can't be more specific with you on that question because it's really just all about the context clues in the question on the test tomorrow. So you just have to really read carefully. So if it's something like HSO4, you really have to read, is the question asking you about it in terms of an acid or a base? And so those context clues were, if we were asking this in terms of an acid, we would ask for what conjugate base would it make? If we were asking for it in terms of a base, we would ask what conjugate acid we would make, or we just give you the whole reaction. So I'm really sorry I can't be a little bit more specific, but if you still have questions on that, please swing by tomorrow morning. I can probably explain it a little bit better in person. All right, we've reached the last question of the day. So if you've got a question, you've probably got about a minute or so to get it submitted before I go ahead and sign off for the night. But our last question is, how would you find an equivalence point? All right, how you would find an equivalence point is we would have to give you an indicator and we would have to give you a pH meter to actually go ahead and do that on the test tomorrow. So we're not going to do that. So what we will do is we will do things like assume that the equivalence point is going to be met in the test. So we would say, given this reaction, you know, what would the pH or what would the concentration be at the equivalence point? So we're just assuming that the acid and base moles are going to react with each other to the equivalence point. We do the math based off that. Or if we're giving you a data table, let's pretend I gave you volumes for all this stuff. We're just going to assume that that volume is at the equivalence point. The only other way we could ask you to find the equivalence point would be to give you a graph like this, like we did on the review packet. Where is that graph? The equivalence point on a graph like this, remember, is going to be when the line goes straight up and down, because at this point we're so close to having H plus and OH minus equal that it shoots right up, skyrockets. So the equivalence point would be the middle of this up and down part. You just follow it straight down to the x-axis, and that's how you can get the volume for that. So that would be the ways that you would be able to find the equivalence point tomorrow. And that appears to be all the questions that I have this evening. If you have that last minute question in, I will be talking here for just a brief second or two to give you the opportunity to fill in that last question. But I will be in school early tomorrow morning for any other questions that come up tonight as you are studying, whether you're reviewing your homework problems that were due today in class or going through old labs or trying more of the review packet. We will be there tomorrow morning to help you out with those. But I hope you found this broadcast helpful. If you have any suggestions about how to improve it or make it better, please feel free to let me know. I'm always looking for ways that I can improve stuff like this. This was recorded, so the link will be live afterwards with a video of this. And if you have any questions at all, you can always shoot me an email later tonight or swing by tomorrow morning. Good luck, guys. I know you guys are going to rock it, and have a great evening. Bye.